So now let's try to prove this main theorem. Basically, the commutability implies, if and only if your conditional expectation is faithful. So first of all, if you want to show the forward direction, so assume your P is Nika immutable, so your full and reduced are the same. Then to show the conditional expectation on the full is the faithful is essentially the same as showing the conditional expectation on the reduced is faithful. Okay, so let's just consider the reduced one. Okay, all I need to show is that is faithful. Okay, so let's consider that conditional expectation. So what it does is that if you're given lambda p, lambda q star, that's lambda is a left regular representation, it can map to the phi of this is just equals to delta of pq, Kronecker delta, lambda p, lambda q star. So only when p and q are the same, you get your lambda p, lambda q star back. Right, and so one thing is that, well, because all of these lambda, this left regular representation are on the L2 space, let's just consider for every x inside your P, and let's consider the basic vector Ex inside the L2 of P, okay? And so suppose let's just consider what happened when you try to do the lambda P, lambda Q star, when you apply to Ex and the inner product with Ex. All right. Well, this one, well, of course, the lambda q kind of try to translate x by q inverse, and if can, then it kills off. But another thing is that because your e's are also normal to each other, the only chance is, well, this lambda will shift this e to some other basic vector, and the only chance you get a non-zero inner product is when this inner product, well, the first coordinate still give you a ex, okay? That's the only chance, okay? If it shifts to any other vector, then you get something else. And the only chance you get shift from ex back to ex is when p and q have to be the same, okay? So if p and q are different, then there's no chance your ex, when you apply lambda p, lambda q star to ex, it still give you something along the ex, okay? So this is essentially equals to the delta x, delta pq, okay? Only when they're the same, you may have a non-zero value. I'm not saying it's always non-zero, depending on whether your x is inside the range of q, but still, if your x on p and q are different, then it's certainly going to zero. So you can put a delta here. But this is just equals to the phi of the lambda p, lambda q star applied to ex and ex. And all of these lambda p, lambda q star are dense in your reduced C-star algebra. We saw it from last time because let's follow from the Nika covariance. So what I essentially showed that is that if you apply phi to anything, and you try to take a ex and inner product with ex, it's the same thing as you don't apply this phi at all. Okay, so in other words, for every say t inside your the reduced C star lambda of p, if you apply phi t, if you inner product take a ex inner product with ex, that's the same as t of ex inner product with ex. Okay. So well, this is very nice. Well, now let's see why this phi has to be faithful. So for every b inside your C star lambda of p, okay, this b, well, if you have consider b star b, and I have a phi of that, apply ex and the ex, okay. So if your phi is phi of b star b is equal to 0, okay, so then that part is certainly equal to 0. But that will imply that the b star b of ex inner product with ex is equal to 0 as well. But this one is just no other than norm of bex. Okay, move the b star to the other side, and this is b of ex inner product with bex, and this is just its norm square. So if that goes to 0, then it just means bex equal to 0, but that's for all x inside your p. Remember, your b is a very concrete operator on the L2 of p. L2 of p, the autonomal basis consists of these ex, and your b will kill off all of them. Well, so b has to be the 0 operator. Okay, so that just implies b is equal to 0. So phi is faithful. Okay, so this is essentially also shows that the conditional expectation, if you do the same thing on the reduced C-star algebra, then it's always a faithful conditional expectation. All right, and now let's go the other way. So suppose I have a faithful conditional expectation. So this is actually, I described it from last time. So you have your full one, and then you map it to the reduced one by this left regular representation. And to show that's injective, well, you compose with this faithful conditional expectation on the diagonal algebra. You know, this part is faithful on these positive elements. And you can do the other way. You write using this big phi, and it maps into d of u, which is the same as d lambda. We saw that. And your big phi is also faithful on conditional expectations. Okay, faithful on on positive elements. All right. The only chance that happens is that your lambda has to be faithful. Okay, so in other words, so if your lambda of some say b is equal to 0, okay, then of course your lambda of the b star b is also equal to 0. And you fit it into the phi. Well, so you fit into this phi of lambda b star b. Okay, that's just equal to 0. So but this phi is just essentially can treat it as the big phi of the b star b. Okay, let's pretend this big phi maps from the full to the diagonal of the full, but the full you identify it as d lambda. So this is essentially just phi of b star b. But phi is faithful, so by the faithful, this phi is faithful on these positive elements. You obtain that b is always equal to 0. Okay, so that's the easier direction. Right, so now we just have this nice characterization of amenability, and let's try to use this. Of course, we have a condition. Okay, faithful conditional expectation. So how do we use it? So I want to prove two things. So first of all, in this video, I want to prove that the abelian semigroups are always amenable. So if your P embed, let's say P is a quasi-lattice order, let's say P is embedded inside some abelian one, so G is abelian, then you have a nice amenable semigroup. Okay, so P is Nika amenable. Okay. So that's particularly very nice. Well, because remember when we first talked about semigroup C-star algebras, if you just take the n squared, okay, basically the free abelian semigroup generated by two generators, if you take the universal one to be all the commuting isometry, then that's not going to be isomorphic to the reduced C-star algebra of the n squared. Okay, so that's a very bad result. We don't like that. So it seems like Nika amenability will fix that. Okay, so at least all the abelian ones, we know they're going to be Nika amenable. Okay, so here's a really nice proof actually. So everything here is discrete topology, so I don't need to worry about G being locally compact, so they're all discrete. So because they're discrete, my G hat is going to be compact. Okay, so I have a abelian G, so it has it's discrete, so it's compact. I can talk about dual group, and so for every let's say gamma inside my dual group G hat, I can define some kind of twist of my universal representation. So I say theta of gamma of some my universal one, the IP is the universal representation. So what I do is I just twist it by this gamma of x, okay, and then I put IP of x again, okay. This one is easy to see. Is again a Nika covariant representation. Well, the reason is that I just multiply this isometry by a scalar and not really changing its range. Okay, so these guys, they are going to be Nika covariant representations of my semigroup. Okay, I'm just twisting it. And because it's Nika covariant representation, so by the universality of the universal C-star algebra, this theta really just extends to a C-star homomorphism. So I map it from the universal C-star algebra. Well, its range is clearly still inside the universal C-star algebra of the semigroup. What it does is basically doing this twist. Okay, I mapped it to gamma x, IP of x. All right. All right, so this is going to be, well, it's going to be invertible, so everything is going to be a star automorphism. Things are, you can easily check, it's also very continuous. So now what I can do is when we have this kind of automorphism is that I can do an integral over this G hat. Okay, so for every x inside my full C star algebra, what I can do is that I can define phi x to be the integral of my twist. Okay, the theta gamma of x d gamma. Let's just normalize this d gamma to be a probability measure on G hat. Okay, G hat is compact. All right, so this is the phi of x. Okay, so well, this map, it will map from the C star u to the C star u. Okay, so this is again from the C star u of p to the C star u of p. Okay, so let's think about what it does. Okay, so for every x, if x is given by a things like ipx, ipy star, okay, one of those basic elements, then what I have is that the phi of x is just equals to the integral over g hat. So the ipx will contribute a gamma x. Ipy star, well, ipy will have a gamma of y, and so when you take the star, you get a gamma of y conjugate. All right, and or you can think about gamma of y inverse, same thing. But you have ipx and ip of y, okay, ipy star, and then you do d gamma. This part really just doesn't depend on gamma. So you're just integrating so this is essentially just integrating over g hat of gamma, you can say xy inverse d gamma times dx. Okay, so this is just dx. Okay, it doesn't depend on gamma. But when you try to integrate a character, okay, you fix some value, and then when you try to integrate a character, if you recall what we did earlier this term, we talked about the character of these billion groups when you take the integral. Most of the time you get 0 when you're trying to integrate over something, when you evaluate something that's non-identity, okay? If you're evaluating that identity, then of course you get a 1, okay, because your G hat is probability measure. So it's equals to x if your xy inverse is equals to the identity. In other words, x equals to y, okay? So i.e. x is equal to y. And everything else is just equal to 0. And you can see this phi is just a conditional expectation, okay? It just kills off the off-diagonal entry, okay? This phi, first of all, is integrating a bunch of also a star automorphism, so this is certainly a contracted map. It kills off all the off-diagonal entries. So this is the conditional expectation. And why is this going to be faithful is really just because this theta of r, or theta of gamma, because they are star automorphism. If the b star b is something positive, then theta r, well, theta gamma of the b star b is still going to be positive. So if your conditional expectation is equal to 0, well, it just means, well, you're integrating a bunch of theta gamma of b star b, okay, over this g hat. Let's say d gamma, that's also going to equal to 0. When you try to integrate a bunch of positive operators to 0, okay, so it just means your function, your operator are essentially just 0 almost everywhere. So that just implies that theta gamma of the b star b, well, that has to be equal to 0 for all gamma. Okay, so in particular, your b star b is equal to 0. Okay, so and that just implies b has to be equal to 0. Okay. So this finished the proof. Okay, so we show that all the abelian semigroups are going to be, well, if they're sitting inside a abelian group, then they're automatically Nika amenable, which is very nice. Okay, so we solved, for example, the n squared and so on. They have to be Nika amenable. So I just want to mention as a fact that if your group satisfy or semigroup satisfy the following, so for every xy inside your P, there exists a least common upper bound inside your P. In other words, there's any two elements always have an upper bound. Okay, so Nika quasi-lattice solder said they have a least common upper bound, and if that happens, then this P being amenable, P is Nika amenable. Amenable. That's actually if and only if the underlying group is amenable as a group. Okay, amenable as a group. So that just implies, well, that's kind of the connection when you try to connect from the semigroup to group. But this doesn't answer the question if this condition doesn't happen, okay? And in the next video, we're going to show a very surprising thing for this Nika amenability. But before I do that, I just want to give one example. Let's say one example. So from there there are semigroups that are not Nika amenable. So one example is coming from this class called the braid group. I'll just quickly write what they are. So the braid group on 3 strings are basically given by 2 generators A and B. They satisfy a very interesting relation. So they have ABA equals to BAB. Okay. So what do you think about is that the braid group really comes from you permute the strings. Okay, you try to braid them. So this is A. And the other one is B, so you try to do B, and from there you kind of swap the position of these 3 strings, and you got a group called the braid group. This is not amenable. Okay, this is not amenable because it contains a copy of the free group. You can think about why. But as a result, if you can consider the semi-group, which is just the semi-group generated by the same kind of generators that's sitting inside B3, that's actually quasi-lattice ordered. I'm not going to show that, but then that's a typical example of quasi-lattice ordered semigroups. So this is also satisfies any 2 element has a common upper bound. Okay, so this satisfies for every x and y inside your B3 plus, there exists a least common upper bound not equals to infinity. So that just implies this. I have one example of non-Nika amenable semigroup. Okay, so it's not Nika amenable.